Start the Chemistry 1 review, and yeah, this is a Chemistry 1 review. If you're not here for Chemistry 1 or you think you're in another review, it's Chemistry 1. That happened to me on Sunday. So disclaimers: if anything, like if I'm doing a problem and you're like, this is iffy, like you're questioning how I'm doing it, just go ahead and raise your hand. Sometimes mistakes are made. So I'll go ahead and assess it at that point and see if maybe like, oh, sorry, it was supposed to be this point at this way. And also, definitely study more than just this material. This is just some of the really main points, or I feel like points that are easily skipped through. So I put a focus on that, but there's definitely still more material than what I included. And if I'm writing off the page and you can't see what I'm doing, just scream at me and I will move it. So let's start. So the first part of the review is going to be a mixture from chapter 1 to chapter 4, but it's not going to be in any order. And I did this so you can feel like you know what it is on the exam when you have to go off and on. So the first problem says, the proton has a radius of approximately 1 times 10 to the negative 13 centimeters and a mass of 1.7 times 10 to the negative 24 grams. Determine the density of a proton for a sphere with a volume of 4/3 pi radius cubed. So this is a simple density problem. It's just using a proton that has a shape of a sphere versus a given volume. So when we're looking for density, that's going to be mass over volume. And the units that you're going to look for density are going to be based on what most of the time what the answer choices are, if it's not because it's a multiple choice exam. So, but most of the time in Chemistry 1, you're going to be dealing with grams over centimeters cubed. And centimeters cubed is equal to what? Great, milliliters. So that could also be grams over milliliters. So here we're just going to go ahead and our mass is already given to us in grams, so we don't even have to worry about converting that. We just have to find the volume. So we'll go ahead and do 4/3 pi, the equation, and now we're going to fill this in to what's appropriate for us, which is just replacing the radius term, which was given to us as 1 times 10 to the negative 13 centimeters. And once again, because that's already in centimeters and we're looking anyways to have centimeters cubed, you do not have to change it. But if it was in meters, you would have to go and do that conversion first and then insert it into the equation. So we'll get this volume, and on tests, I like to save time. So since I already know this is my volume and my density is going to be right on top, I'll just go ahead and put my mass on top of this. So it'll be 10 to the negative 24 grams. And then get whatever, put that all in the calculator and get that volume. Get whatever answer that is, because that's going to give me straight my density answer, which would be 4.06 times 10 to the 14 grams over centimeters cubed. So, yeah, I remember professors usually like doing density this way because it makes you think of volume in a different aspect. So, good for everyone? Okay. Now we're going to be talking about natural abundance, which this feels like years ago. So the question's saying silicon has 3 naturally occurring isotopes. It tells us the isotopes, and then it's going to go ahead and tell us the mass and natural abundance of the first isotope, which is silicon 28, and it gives us the mass, which is 27.9769 AMU. And what does AMU equal? Or AMU? Remember? Awesome. Yeah, that's like the number that you find on the periodic table. So grams, if this said grams per mole, is that the same thing? Great. So And then it gave us the percentage of that is found, 92.2% respectively. And it says the mass, not the mass, and natural abundance of Si29 are 28.9765 mu and 4.67% respectively. What is the mass and natural abundance of the isotope that we don't have the information for? So first off, we know that, especially if you see like we're working with percentages, that the isotope in total is going to have to equal like 100%. So if we already have 92.2% for Si28 plus 4.67% for silicon 29, then our missing percentage for silicon 30, but we know this is all going to have to end up equaling 100% for silicon. So once you like rearrange that and you subtract what you added from 100%, that'll give you I don't have another color pen, but 3.13% for silicon 30, which is what you need to figure out now what the natural abundance would be. So this is that formula from, like I said, what feels like years ago. That is the atomic mass of an element equals the mass of the first isotope times its natural abundance. Abundant. Oh my gosh, abundance. There we go. I'm good at chemistry, not reading or writing. So natural abundance plus, now you're going to keep doing that for all the isotopes that you have in total. So it'll be mass 2 times percent, and I'm just going to say Na for natural abundance divided by 100, and you're going to keep going. In this case, we'll go up to 3 because we have 3 isotopes. So, and if you notice, I'm dividing the natural abundance by 100% because they gave us our abundance in a percentage, and we want it in fractional abundance when we're doing the atomic mass of the element. So you're going to have to divide it by 100% to give us fractional abundance. So once you set this up and fill everything in, you would end up equaling 28.086 mu. And this is the mass of silicon in the periodic table. And that's going to equal, and then you're just going to set it up, 27.9769 mu equals 92.22 divided by 100. And please, on your calculator, don't do 92.22% divided by 100 because that might throw off your number. You dividing it by 100 is already taking it from the percentage to the fraction. Plus 28.9765 mu over 4.67 divided by 100. And then now this is the one we're missing, silicon 30, but we already figured out its natural abundance from our equation before, so that's 3.13 divided by 100. In total, once you distribute everything, you'll get 0.938 mu equals silicon 30 still times that 0.031. See, that's now our fractional. I put an extra 3. Oh, whatever. There. So in total, we'll have 30 mu. And this isn't to the correct amount of significant figures, but keep that in mind when you're doing this. I did these calculations quickly. Look good to everyone? Ring a bell now? Okay. Now, this is just a quick review on the laws, because especially I feel like the ACS actually likes for you to know things like this. Like they might throw in like some comprehension questions in there, or like concept questions. So this is just a quick review. And the law of conservation of mass, we know that means that matter can't be created nor destroyed. So matter can't be created nor destroyed. And it can only be transformed, which makes sense why we're conserving it. So it can only be transformed. And then our law of definite proportions tells us a given chemical compound always contains its component elements in a fixed ratio by mass. Chemical compound. I'm writing these all down so you guys have, this to reflect on, so you don't have to go through later and pulling it out. So given compound always contains its components elements in fixed ratio by mass. And M is going to represent mass. And then our law of multiple proportions tells us when two elements combine with each other to form more than one compound, then the ratio of masses will be the ratios of small whole numbers. So we have two elements combining. They form a compound. So what do we know is going to happen? The ratios of their masses will be a ratio of small whole numbers. I'm trying to like shorthand this, but these laws were not meant to be shorthanded. Small whole numbers. Now, the atomic theory that I will leave for you all to go ahead and write, look for it after on your own, but I will talk about it because the atomic theory, if you remember, had a few components to it. And the 4 parts were that all matter is made of atoms. All atoms of a given element are identical in mass and properties. Compounds are formed by a combination of 2 or more different kinds of atoms, and a chemical reaction is a rearrangement of atoms. So if you didn't remember all that, then you could just go back through your notes and look for that one specifically, so that we could get through the rest of the material. So now our next question is taking what we just talked about, these laws, and applying it, which this is more or less what you would get from a question, remembering what the laws were and then how to apply it. So when hydrogen and oxygen react, the mass of water formed is exactly equal to the mass of hydrogen and oxygen that reacted. Which law is this consistent with? Can anyone tell me? Awesome, yeah. So this is going to be the law of conservation of mass, and which makes sense because it's talking about that even though now we had something that reacted, the same amount of mass is still there. The trickier ones sometimes to distinguish between are the law of definite and law of multiple, since they're both with ratios. So look back at those. Now we're going to go to compound naming. So when you're naming a compound, the first step, as soon as you see one, would be to determine whether it's ionic or molecular, and even if it's an acid or base. Because specifically between ionic and molecular, that's like a bigger focus, that's going to determine completely now the rules that you're going to follow to name it. So, and what's a quick way of determining if it's ionic or molecular? We know an ionic compound is going to be a mixture of a metal and a nonmetal. And a molecular is going to be 2 nonmetals. And where are metals and nonmetals located on the same place on the periodic table? No, right? We have metals on one side and nonmetals on the other side. So most of the time, if they're really far apart, you're going to see that's ionic. And specifically, though, following that rule, metal of nonmetal. So our first compound is we have 1 tin and 4 chlorines. So we know that tin is a metal and chlorine is a nonmetal. So this is going to be an ionic compound. So when we're looking at ionic compounds, we have to think about is the metal going to be an ion that can form like more than one charge, and tin can form more than one charge. So because it could be a cation that can form more than one charge, its name is going to be associated with the charge that it's going to have to carry. And then chloride is going to just be chloride and not tetrachloride, because like we said, we're dealing with an ionic compound, and ionic compounds are more about, when you're thinking about the name, it's like making sure the charge is like known. I don't know how to explain that in a better way. But yeah, so that's why. And how did we know that the charge on tin was going to be 4? Because chloride carries a charge of -1. So if we have 4 chlorides, we're going to have a -4 charge. So we need a +4 charge on the metal to make that a neutral atom. So it'll be tin 4 chloride. Now our next compound is sulfur with 3 oxygens. Both sulfur and oxygen are not metals, so this is going to be a molecular compound. And when we're working with molecular compounds, the way to think of this is, I'm going to put this like little chart on the side, is you're going to have a prefix, then the name of the first element, and then the prefix again, with the name of the second element, plus "-ide" as the suffix. So following that, we only have one we only have one sulfur, so we're not going to need a prefix on that because it's the first atom as well. So because it's one atom and it's the first atom, we're not going to put a prefix on that, so it's just going to be sulfur. Plus, we have 3 oxygens, so it's going to be tri. And we're going to change we're going to drop the suffix of oxygen, so the GEN, and change it to "-ide" to give us sulfur trioxide. Now, for our next element, this compound, this is going to be barium with a nitrate group, which is a polyatomic ion. So polyatomic ion, yeah. Because when you're, why isn't the second one sulfide? Because you have to put the first compound doesn't get changed, doesn't get the "-ide. It's the second one in the group. So it'd be sulfur trioxide, because the oxygen gets the "-ide" enzyme. Yeah. I'm sorry, what?
Like, I think she's saying the polyatomic ion sulfide, like SO3.
Oh, well, sulfur trioxide, this is a molecular. That's true. That's the sulfide. You're saying the polyatomic ion? Let me look that real quick, because when I pulled this example, I didn't see that. And I'm sorry, off the top of my head, I do not know all of the polyatomic ions. Even though it wouldn't even be sulfide. Yeah. Okay, yeah. It's not, okay, yeah. When it's an ion, then like when it has the charge on it, then it would become, actually I think it's sulfate, not even sulfide. Okay, then it'll be sulfite, ITE. Yeah, but that's when it has the charge on it. Because this is just a molecular compound and it's SO3, and when you draw the Lewis structure, it can exist without being an ion, it's going to be sulfur trioxide, which is different when it has a charge. So that's why that charge is really important. For a second, you made me question everything I knew about chemistry, but it's okay. So, good with everyone? Okay. Now the next one, we are indeed working with a polyatomic ion, which, because this is a polyatomic ion, like I said, we're working with nitrate. And nitrate on its own looks like NO3 with the negative charge on it. And then we have the metal barium. So this is going to be an ionic compound. So we're going to do the same like thought process that we did on the last time. So this is going to be, to make it neutral, our barium is going to need a 2+ charge because our nitrate has a -1 and we have 2 nitrates. So to get it neutral, we're going to need a 2+ with a -2. And barium can exist as Ba2+. So we don't have to worry about the number like behind it. So that would just give us barium nitrate, because that's the only type of cation barium forms. Okay. And then lastly, this is another molecular compound. So you're going to follow the chart, and it's molecular because both nitrogen and iodine are nonmetals, and then you're going to follow this same chart that we discussed. So nitrogen is the first atom. It only has 1, so it's going to be nitrogen. And then we have 3 iodines on here. So we're going to add tri to it again. We're going to keep the beginning of the iodine. So this is going to look weird because now we're going to have 2 I's next to each other. And we never see that, I feel like, in our language. But if you do indeed keep the I from the I from the tri and the I from the iodine, and then you're going to change it to ide. So, and that's the naming of compounds. Now, the next problem, this is also from back in chapter 1, and this is asking what is the amount of moles of oxygen in a 24.1 sample of carbon dioxide. And this is actually a very straightforward problem. It just might feel weird if you haven't seen it in a while. But all this really is asking for you to think about the moles of carbon dioxide you have, which is 24.1 moles of carbon dioxide. And then to know how many moles are of oxygen, you know you have two moles of oxygen actually forming the carbon dioxide in period, that's that ratio. So based on this sample, you just have to set up 24.1 moles of carbon dioxide times 2 moles of oxygen for the 1 mole of carbon dioxide, and that'll give you 48.2 moles of oxygen. No. Yeah. Yeah, I was looking right now at this, and no, it wouldn't. It would not be 48.2 moles. Like I was looking, I don't know if you guys all saw my silence. I was like, wait, no. Okay, and that's a disclaimer I gave in the beginning. So this would, and the red flag to me that showed me something was wrong was there's no way you're gonna have more moles of oxygen. You can have a bigger sample of oxygen than the total mole sample. Like that wouldn't make sense. That's how I immediately knew this was wrong. So because oxygen is diatomic, I think you'd have to think of this as like 1 mole so that you'd get the equal ratio. But I really don't like this problem right now, so I'll look back on this and then think about it again because I don't like this problem. So look at another problem on how oxygen like relates in samples, and I'm gonna go ahead and by like the hour out of here, I'll put how to solve this on with a different example. Sound good, everyone? Okay. Yeah?
Is that how you typically solve this stuff? Is that a problem?
Yeah, that's why, because what this is like asking is, it's doing like a conversion from like like the oxygen in the total compound. So this is how I would like usually set it up, but I don't know why. This is definitely not the right answer. And right now with this pressure, it won't come to my head, but it's okay. So if anybody wants more conclusion, like more of an answer on that, just talk to me at the end. Okay. So this question is asking in an acid solution of 1 molar in HCl and 2 molar in sulfuric acid, what volume of 0.150 molar of KOH solution will completely neutralize all the acid in 500 milliliters of this solution? So here we have to think about how many moles of acid we need to neutralize the moles of base. So, and in this case, we'll start to figure out, because the acid that we could start with is looking at the sulfuric acid. So we'll think 0.200 molar of H2SO4 is going to contain, like when you think of a molar conversion, what's the equation for molarity? Great, mole over liter. So if you don't have, what 0.200 m is really saying is you have 0.200 moles in 1 liter. So if we have 0.200 moles of proton ions, while we have a point, okay. So what our problem is really saying is, I need another paper for this.
This will be the M1, V1.
No, you have to think about you have to look for how much base you're looking for to neutralize the product. So you're playing with the molarities to figure this out, but I'm gonna need more space to solve this because I can't like get all my thoughts together. Okay, so here. So the first thing I'm going to do is figure out like how many moles I'm working with based on the molarities that I was given. Because we know at the end the moles of H plus from our H2SO4, and let me show the problem here, plus the moles of H plus from our HCl is going to equal the moles of base from KOH, because that's what neutralization means. And we have to take into consideration both of the acids that we're working with to equal the moles of the base. So because, like I said earlier, from the molarity, we know we're going to have 0.200 moles of those hydrogen ions coming from our H2SO4, and then from our HCl molarity, we know we're going to be getting 0.0500. So that would look like this. Hydrogen plus HCl. And the reason why we're getting (0.500) from HCl, even though our I'm sorry guys, this is what happens when I solve things my own way and I'm also referring to something else. So that's why I don't like what's happening right now, but I'm going to do this how I've learned, and then we're going to reflect it based on the other thing. So this is going to be, because we just got our moles from the this acid, now we're going to do that same process to get our moles from our hydrogen, from our other acidic solution, which will tell us that there's also 0.100 moles. So this refrain from of H plus from HCl. Is that how everyone, like when they're going through this, got this, or? Yeah, okay. So then once 0.200 plus 0.100 is going to tell us that there's 0.300 moles in total of our protons. So we're going to need 0.300 moles of our base. And now to figure that out, we know the molarity of our base was 0.150 KOH. So we're going to make that equal to the 0.300 moles that we needed to find what our volume is. And then once you do that, the volume would equal, I don't have a calculator on me. Could someone do it point, like, you would have to multiply now V times 0.150, so it'd be 0.300 divided by 0.150. What answer do you get for that? Great. So then the volume would be 2 liters. Yes. Yeah, so, oh my, thank you for pointing that out. Honestly, guys, I just got so, like, in stress mode, and I apologize because I know you guys are here for a review, so you expect the best, but that I shut down and completely didn't see that part of the problem. So yes, thank you. We have to take that into account now. So taking that into account, you're going to do that same process. But because it is saying that we only have the 500 milliliters of the solution, of the acid solution, you have to think about what the smaller amount of moles is going to be, because now that's going to like dictate it. Which that's why we get that 0.0500 moles from the HCl. So you would do all of this, but with moles, with 0.0500 moles of H plus for the HCl instead. And once you do all those calculations, it ends up to really be 1.67 liters. I know that was really confusing, so if I just lost all of you guys, I'm sorry. Do you have any more questions? Huh? No? You're just confused? Okay. Okay. Because to completely neutralize the moles of the acid, it has to equal the moles of the base. That everybody gets, right? Okay. So because we have 0.200 molar of the acid, that's going to, from that number, we're going to know it's going to be, and using that we're given only 500 milliliters, would have to convert, like, first of all, we're going to want to like put this into liters, so we could also think about that. So then 500 divided by 1,000, that'll give us 0.05 liters. And then using that is how we also apply to understanding what is in oh my gosh, okay. So now, because we know we're working with actually this is 0.500 liters. We know that the number of moles, you guys, I'm going to start this problem one more time from the beginning. If I can't if I can't explain it correctly, we're just going to keep going. But I feel really bad that, because this is a really big concept on the exam. So, to start off with, because the volume that we were given is that 500, now when we're looking at our molarities, we have to take that into account. So our 0.100 molar of HCl and our 0.200 molar of H2SO4, we need to adjust this for the 500 milliliter solution we have, which the 500 milliliter solution is going to equal 0.5 liters. So when you adjust that, you're going to do 0.200 molar times and because molar is moles over liter, you could just multiply it by 0.500 liters to get the amount of moles you need, which is 0.100 moles of HCl. Then once you do that, you're going to do the same thing for the HCl. I just did this for H2SO4. You're going to do that same concept for the HCl, which is going to be 0.100 molar times 0.500 liters, because that's the molar that we have for HCl, and that's going to give us that 0.0500 moles of HCl. Then once you have that is when you do the next yes. I'm sorry, can you again? What do you mean mole ratios? Well, more than anything right now, the equation's not really gonna affect us too much in this instance, because what you're really trying to find, and the reason why before you guys were confused because I didn't adjust it for the 500 the solution, is you're trying to see how the molarity that you already have, how you're gonna take the amount of moles based on now the new solution you have. Like you're gonna find the amount of moles you have using the molarity and the amount that you're being able to use to neutralize it, to then find how those moles are going to equal the base. Yeah. Does that make way more sense to everybody now? Yeah? Okay. So once you do that, that's when you'll do what I just did earlier. I just did it with the wrong numbers. The moles of the HCl plus, oh my gosh, I keep interchanging this, H2SO4 plus the 0.0500 moles of HCl, and this is going to give you that total of the total that you need to understand of the base. 0.150 moles of base, and then that's when you do that other step of taking the molarity of the base and then equaling it to these amount of moles. And that's when you get the 1.67. I sort of want to move on from this question because I know we have a lot of time. I mean, we only have a certain amount of time, and I really want to get to the gas stuff. So does that new explanation make sense to everybody? Yes, okay. Our next problem is asking us, we have a sample, a 7.83 gram sample of HCN that contains 0.290 grams of hydrogen and 0.406 grams of nitrogen. Find the mass of carbon in the sample. That's 3.37 grams. So this is really a problem dealing with the law of definite proportions, which is telling us that all samples of a given compound, regardless of the source or how they were prepared, are going to have the same proportions. So if we have a 783 grams, if we have a 783 gram sample and we know it has this much hydrogen and this much nitrogen, then that means the mass of the carbon of the sample is going to equal 783 minus 0.290 grams of the hydrogen plus the 4.06 grams of the nitrogen, which is going to give us 3.84 grams. But now we need to determine the mass of the carbon in the specific sample. But because we know that law of definite proportions, we can do the mass of the carbon over the mass of the sample, which would mean 3.48 grams over 7.83 grams, and that's going to give us 1 over 2.25. Now, we know the mass of the second sample is 3.37, so we could use this ratio that we made to figure out how much, so then you would set up this to look like the mass of the carbon over now our new sample, which is 3.37. And we're going to use the ratio that we just made, which is 1 over 2.25, to give us the mass of the carbon to be 1.5 grams. Good? Okay, I'll keep that for anyone still making notes. Now, the next question is asking, what is the mass in kilograms of a 5.48 times 10 to the 29th sample of lithium atoms? So here, all we really are doing is we're taking the number of lithium atoms given to us. We're going to do a conversion to the moles of lithium to then give us the grams of lithium, to then give us the kilograms of lithium. And I always say this more than anything is a lot of the questions that you're given, no matter what the topic is, most of the time what they like to do is make you apply what you know, and then they love to throw conversions in that. That's like the number one thing maybe is always throwing like like a conversion that you wouldn't really think you have to do. So always pay attention to your units. So first we'll do the 1 mole of lithium. This is how this would be completely set up. And because we're going from atoms to moles, we're actually going to be using Avogadro's number. So we know that I just want to set this up the whole like long way. So 5.48 times 10 to the 29 lithium atoms, and we're going to multiply this by our ratio that we know for Avogadro's number, which tells us 1 mole is going to have 6.022 times 10 to the 23rd atoms. Then we're going to multiply this by the molar mass of lithium, which would now cross out our moles, but we don't want it just in grams. We have to keep going. So to get to kilograms, we're going to have to multiply it. We'll actually divide it by 1,000 grams to get kilograms. So then we end up with 6.32 times 10 to the third kilograms. And if you'd like to see how things like cross out, it would be see, atoms here cross out, moles here, grams here, grams here. Great. So a substance has a density of 1.11 grams to the centimeters cubed. What is the volume of 0.41 kilograms of this liquid? Once again, this is just you thinking about density and what it really what units you should be having. So we know we're gonna have to convert our mass, which is 4.1 kilograms. We're gonna want that in grams. So to convert this, you're gonna put this to divided by 1,000 grams, and 4.1 divided by 1,000. What is that going to give us? And when 4.1 divided by 1,000? 4.1 times 10 to the negative third? Great. Kilograms. Grams. Now, once we have that, there's two ways you can do this. Some people like to plug and chug. I actually like manipulating my equations. So if I know density equals mass over volume, I'm just going to change my equation of density to equal volume. So if I'm doing that, I'm going to get volume equals mass over density. So now you just have to insert what you have, which is, it'll be V equals 4.1 times 10 to the negative third grams divided by 1.11 grams centimeter cubed. And that should give us approximately, I think it'd be like 369. In the last one, I did what? So when you're doing conversions, when you're doing this, you could do it based on your preference actually. So like when I do from grams to kilograms, I always do it, oh, you mean because I put 100 instead of 1,000? Yeah, okay. But yeah, you can still do it this way. You don't always have to do 10 to the third. You can still do it. It looked like there wasn't a 0 there because when I crossed it, but you can still divide it by 1,000 grams, and that's the same as doing it the other way. Yes. Oh, okay, okay. On this part. Yeah, yeah. So this would be 1 kilogram times 1,000. So it'll be 10 to the third instead. But you guys understand the process, right? So then this would be 4.1 times 10 to the third. Divided by 1.11. What did you get? Thank you. 3,693. And this is going to be in centimeters cubed, which is also equal to milliliters. But they want it in liters, so when you convert this to liters, you would get 3.69, but based on significant figures, it would be 3.7 liters. Okay. Now, this is just an isotope, and remembering that an isotope is the same amount of protons, but a different number of neutrons, opposed to an ion, which is the same amount of protons, but a different amount of electrons. So when you're reading this, you know that the atomic number is going to be this portion right here. So we know our atomic number, which is also sometimes represented by Z, is 88. And our atomic mass number is the one on top, which is sometimes represented as A. This is A over Z. Is going to be 226. Now, what does our mass number also tell us? It's also going to tell us that the number of protons. So if we have 88 protons and we know our mass number is gonna equals what? Great. Our mass number is going to equal the number of neutrons plus protons. So we know we have 88 protons, and now to find neutrons, we'll do 226 minus 88, and that would give us 138. So this is like a review from like chapter 1. Next, we have, this is finding the empirical formulas. So we have a 45.2 milligram sample of phosphorus that's going to react with selenium to form 131.6 milligrams of selenide. What is the empirical formula of phosphorus selenide? So we know the amount of phosphorus in the sample. Is going to equal 45.2 milligrams. And the total amount of the mixture is 136. So if we want to know the amount of selenium in the mixture, you're going to do the total amount, which is 131.6 milligrams minus 45.2 milligrams, because that's just of the phosphorus. So we're going to get 86.4. milligrams. Now, we're going to want to figure out now that we have the separate masses of both of them, how many moles we have of both of these elements. So to find the number of moles of phosphorus, you actually don't even, I keep showing phosphorus wrong, but you actually don't even have to convert it to grams first. You can just go ahead and do the conversion of moles. So this would be, to find the number of moles, we're going to use 45.2, and actually you still do have to do it. What I meant by like, if you're really comfortable with your like converting rather than like doing a whole second step, you could just do times 10 to the negative 3 grams rather than sitting there and converting it. Does everyone see how that is the same as like doing a conversion? A hopeful one? Okay. So then if we want our number of moles, we're going to go ahead and multiply this by the molar mass of phosphorus, which would be 30.97 grams over 1 mole. But what this 10 to negative 3 still signifies is that it actually, we're still like looking at it as milligrams. So our answer is going to be in millimoles. So it'll be 1.459 millimoles. And the reason why we do this is because you want that like small number. So then when you do this same process for selenium, you would get, doing like the same thing that we just did, it ends up being, but with the appropriate numbers, ends up being 1.094 millimoles. So now you're going to take what you just got from these numbers, and you would make your, like sort of like a fake formula based on these actual numbers. So this would be P times 1.459, and then selenium is Se times 1.094. But you will never see this like this. You want it in whole numbers. So you're going to first take the ratio of which is, so we have less selenium. So this is what's going to like determine what our whole number ratio is. So do 1.459 divided by 1.094, and then the same over here. So here we're going to get 1, and here we're going to get 1.3. So now we're going to make our simple ratio, which would be P to the 1.3 with selenium to the 1. And then you're going to multiply that by a whole number. And in this case, 3 is going to be our best whole number to get an empirical formula of P4SE3. Okay. I'm going to go ahead and skip to like the more important ones on the first. Okay, well, who wants to keep doing like older review things or wants to change already to like the newer material, especially like chapter 5 with the gas stuff? If you want to change to gas, raise your hand. Okay. And if we get enough time after, we'll go back to like this stuff, but I think the gas is way more important because you guys haven't had any practice with that. So, and at the end, yeah. Which, like, with the ones with the answers or the actual review? Yeah, it's online. So when I went to like put it on, I actually put it on Monday and it didn't save the page. And when I went, somebody, like one of my SI attendants was like, hey, where's the second part to review? It's like, it should be on there. But for some reason it didn't save, so it's like on there now. Like I checked yesterday. And what I'm going to go ahead and do is whatever parts we don't get to, like even on the first review, I'll go ahead and post those answers up. Like I already have that in the document, so I can post that up with and after so you guys can see that. So now this is like the second part, and this is going to go through like thermochemistry to gases. So this is a delta H of the reaction question, and if you remember, this is when you have to like manipulate the equations that you got to get your total delta H for the reaction, because right now you just have parts of it. So when looking at this, the first thing I'm going to think is to make sure is what I need on the correct sides. So here, this equation gives me my carbon dioxide on this side, and I have my product on that side, so I'm probably not going to have to flip it. But my second equation, the reactant that I need is on the product side. So I'm definitely going to have to flip that because this is my only source of this. So when you flip this, it would look like this. Plus 2O2 gas. And you're going to have to flip now the sign of the delta H. So your delta H is going to equal 1,269.8 kilojoules. Now, we also have to think about, is everything going to cancel out correctly, or does anything have to be multiplied by? So, there's probably like two ways you could think about going for this, but I'm preferably, when I see that I have a 1/2 here, and I already have an oxygen of 1/2 over here that needs to be canceled out, because my oxygen also over here, they both don't end up in the product, like in the overall equation. So to do that, does anybody have any ideas of what you can multiply that by to cancel it out? Actually, this oxygen is going to be, it's going to actually not be 2. It's only going to be like this. So because of that, the simplest way to get rid of this is to multiply it by 1/2. So if you multiply this by 1/2, that gives you 1/2 O2. These would cancel out. You would get, oh, that's where this messed up. There we go. This is supposed to be 2Ca, and this was like, those two units got mixed up. So then once you multiply this by 1/2, you end up with 1 C8 here, CaOO, which is what you need on this side. So this is what the new equation would look like once you multiply it by 1/2. This would be 1 Ca solid plus 1/2 O2. Because this one I already wrote like before it, but this would really be 1/2. So that's what the equation that you'll have to be using would look like. And now you have to do the same for delta H. So when you multiply delta H by 1/2, you end up with, because somebody multiplied this number by 1/2. I think it's going to be like, thank you, 634.9 kilojoules. Now, all you have to do is add, for delta H of the reaction, the total is going to be adding the first one, which we didn't have to change anything to, kilojoules, plus the new one that we manipulated. And that'll give us like negative 177.9 kilojoules. Okay. So this is like the more new material. So here we're going to be dealing with the van der Waals equation, and the ideal gas law. So we have 12 moles of gas, which the equations that we're going to be dealing with, which is the ideal gas law. I'm going to try and write this up here. Okay. The ideal gas law, we know the equation for that is going to look like PV equals nRT. And our van der Waals equation is going to be pressure equals nRT over V minus NB minus N squared A over V squared, where A and B are constants that will be given to you unless the equation gives you everything else and you just have to solve for that. But in this case, this is the A and B that was discussed, like that they gave you. R is a constant, and T is temperature, V is volume, and N is the number of moles. So we know we have 12 moles of gas, so I'm going to go ahead and put on the side note here, 12 moles of gas are in a 5-liter tank. V is going to be our volume, so we're going to need 5.0 liters at 24 degrees Celsius. Now, anything with gas, like, it's a pretty good rule of thumb that you're not dealing with Celsius. You have to convert that to kelvins. So we know when we convert 24 Celsius to kelvins, what does that? It's great, 297. And for this question, I'm going to keep it at just 297. I'm not going to add the 0.15 because you could, depending on the, like, you could use either 273 or 273.15 when you do that conversion. So now it's saying to calculate the difference in pressure using the van der Waals equation and the ideal gas law under these conditions. So first, we're going to have to find it for the ideal gas law. So these are the numbers we got, and they're going to give you R. But I want you guys to know, on the test, there's usually 2 R's given to you. There's going to be 8.314, and there's going to be 0.0821. They change based on their units. So our 8.314 has joules and over Kelvin times moles. We don't want that here. We're not dealing with joules, we're dealing with gas. So in our gas laws, you're usually going to use 0.821 liter times ATM over Kelvin's mole. So keep that in mind, because sometimes, especially on the ACS, they're not going to tell you which R constant you're using in that specific problem. You're just going to have the R constants like in the front page, and you have to pull it. So make sure you're pulling the right one for the right amount of, for the right equation. So then once you do that, you could go ahead and manipulate this problem to equal pressure. So I'm going to do it, which would just be dividing by volume. So be pressure nRT divided by volume. And when you insert all of the numbers into there, you should end up with 58.5 ATM. Did anyone that did the equation already get that? Okay, well, this is going to be for our ideal. Now you're going to do the same thing, but with van der Waals equation. So over here. So now with van der Waals equation, you're going to insert, which is what I wrote up there. You're going to insert the appropriate units. And this one I'll go ahead and like show you guys how you insert it. So this is going to be 12 moles times 0.0821 times Kelvin, which is 297, over now volume again, 5 liters. And that's also a big important point. Our volume is going to be in liters, not in milliliters, because of our constant. So if you're ever confused of what units you should be in, just always go back to your constant and look at what units they're using. That's like a giveaway. So 5 liters minus 12, which is our amount of moles again, times, and now that's that B that they gave us. 0.0430 liters mole, minus now 12 moles squared times A 2.300 over 15 squared, which is our 5 squared. And once you do all that, you should end up with 52.01 ATM. But the question asks for the reason why we had to use both equations is because they want to know the difference in what the pressures would look like. So delta P means the change in pressure, just like this, which is going to be 58.5 minus 58.01, and that's going to give us 6.49 ATM. So with these questions, honestly, everything with the gas laws, it's knowing what equation you need to use, and in this case they told us, and just really more than anything, making sure you have the right units, because that could give you a completely different answer. Any questions on any of these two equations so far? A was 2.300, which they gave it to us here. Okay. So, and if you're wondering what A and B are, in case you remember in lecture, this part of the equation up here is to correct us for volume. It's like the correction in volume of like what a real gas is going to have. And then the A is the correction in attraction. So keep that in mind. Like if they said the constant for correction of attraction, that's the same thing as A. And just think A, attraction. Okay. Now here it's saying which of the following transitions result in absorption of the highest energy photon. So this is from like chapter 7, and we know absorption is it going from a lower end to a higher end, or a higher end to a lower end? Anybody remember? Great, yeah. It's from a lower end to a higher end. So automatically, we know A and C are not going to work because these are going from higher to lower. We don't want that. We want from lower to higher. So if you're like, don't want to do it in your head and you want to do it visually, we know the chart looks like something like this, where n equals 1 here, n equals 2 here. And then as you go up the chart, they get smaller in length. So like in distance from each other. Be like n equals 3 here, n equals 4 here, maybe 5, and even closer, n equals 6. So from 2 to 5 would have a jump like this. From 3 to 4 here, and then from 5 to 6, it would be here. And automatically you see that from, if 2 to 5 was going to be the bigger jump. That's just seeing the visual behind it, but you could have known from knowing 2 to 5 is a bigger difference to see that. The only way it would matter, like, if in magnitude is if, for instance, it's 1 to 3, that's a change of like 2, but that's a way bigger difference than from 3 to 5. So that's why sometimes it's good to think about this chart. So that would have the highest absorption. Now, this is a systems problem, but I'm actually going to jump to another gas one, and then we should have time to jump back to this at the end, but I really want you guys, more than anything, I think the energy, anything with light and gas is like more important, right? Okay. Well, so, and if you do want to jump and do this like on your own, the equation you're using for this is delta E equals Q plus W. Okay. So then here, this is thinking about the shortest frequency of light that's required to move an electron from a sample of metal if the binding energy of the sample of metal is 4.08 times 10 to the 4 kilojoules per mole. So for this problem, you would have to know the equation that energy equals H times V. And this equation is the Planck's equation, where H is going to be our Planck's constant, and V is going to be our frequency. Well, that's like a weird like looking V, but this is frequency more than anything. Frequency. And E equals energy. So once we have that, we know this would be given to you on Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds per photon. So when you're setting up this equation, you have to think about our Planck's constant gave us, it has this photon unit in it. But our energy, our sample, was given to us with kilojoules over moles. So we have to change that to be appropriate to work with the correct units. So what you would do is E equals, you're going to take the number that was given to you, kilojoules per mole. And first off, you're going to go ahead and you want this to be in joules. So to get rid of the kilojoules, and I'll go ahead and do this like the other way that was discussed. You'll put the 1 here, and then you'll put 1 times 10 to the 3rd joules. Okay. So then that's another way of doing conversions. Then you still have your mole factor that you need to account for here. Because we're not trying to cancel out our joules, we're just trying to convert it. So you don't have to go any further. It's just a conversion from kilojoules to joules. But now you need to convert your moles to photons. And what number do we know to use for that? That's when you use Avogadro's number. So you would use Avogadro's number and make it applicable to photons. And this is going to give us 6.78 times 10 to negative 17 joules per photon. And now we could use this in the equation to give us like the correct units. So when you set 6.78 times 10 to negative 17 joules per photon, which is our energy, equal to Planck's constant, 6.26 times 10 to negative 34 joules times seconds over photon times frequency. Once you go ahead and divide that, you'll end up with a frequency of 1.02 times 10 to the 17th negative seconds, which is one of the units for frequency that's able to use. Does anybody remember, is there another way to represent frequency, or is 1 over seconds the only way? Great, hertz. So this was using your knowledge of Avogadro's number to make sure all your units were in the same playing field here. Now, back to gases. This is saying a gas occupies 11.2 liters under a pressure of 0.860 atm. What pressure will the gas be under if the volume decreased to 9,000 milliliters? So the first thing immediately is I see we're working with volume and pressure. So we have a volume 1 of 11.2 liters. We have a pressure 1 of 0.860 atm. and then another volume of 900 milliliters, 9,000 milliliters. Now, we definitely are going to want everything in the same units. So you could choose whether to change, which way you want to change. I personally like to go to bigger things. So I'm going to change this to liters. So when you change this to liters, it'll be 1 times 10 to negative 3 liters. And you're going to go ahead and get 9.003 liters. And here the significant figures are important that you actually keep all those zeros because they gave us that decimal point on the 9,000. So now and what we're looking for is the second pressure. We don't know that. So now this is where you can use that ratio that we know of pressure times volume equals the second pressure times the second volume, and manipulate this equation to solve for our second pressure. BP1 V1 over V2. Once you set everything in there, appropriate, like based on what we labeled, you'll go ahead and solve and you'll get 1.07 ATM for P2. Great. Here's some statements and just thinking about which of the following are true or false. So our first statement says when forming cations, electrons closer to the nucleus are easier to remove. True or false? Great. False, because the outer electrons, which are the valence electrons, are the easier to use, are the easiest to remove. The effective nuclear charge for oxygen is -2. Great, yeah, that's false. The effective nuclear charge for oxygen is actually going to be +6. And that's because Z effective, make this note here, Z effective, remember, equals the atomic number minus the number of core electrons. Or it's representative, and for this, or it's representative of the elements in its column number. So this will be +6. And then valence electrons are easiest to remove. We just discovered that, yes, that is true. The electrons closest to the nucleus shield those further from the nucleus. That is true. And when the effective nuclear charge increases, atomic radius decreases. That is another true statement. And you can think of this by remembering in the periodic table that when you're going from left to right, so you're going, if this was a periodic table right here, when you're going from left to right, the Z effective increases. So this way, our Z effective is increasing, while for our atomic radius is decreasing in that direction because our atomic radius follows a trend that's like this. And a tip I give to people for this is on your periodic table, on the right corner, what's the most electronegative atom? Great, fluorine. Fluorine ends with an E, so I think of electronegativity, and I think of all those things that Z effective, like they all sort of are like dealing with like electric type things. So I just follow that trend, and I know my atomic radius is going to go the other way around, the other way. Now, here, this is which of the following molecules is nonpolar, does not have a net dipole moment. I'll go ahead and do through like 2 of these. So first off, we know HF is going to have 1 electron for hydrogen plus 7 valence for fluorine. So it's going to give us a total of 8 electrons. So when we draw our Lewis structure, it's going to look something like this, with fluorine having 3 lone pairs. So that gives us 1, 2, 3, 4, 5, 6, 7, 8 total electrons on here. So this is going to be polar because there is a net dipole moment. Which direction is the moment going to be pointing towards? Great, the fluorine, the more electronegative atom. So that does have a net dipole moment. Now, when we do our next compound, which is a carbon with 4 bromines, we know we have a 4 electrons for carbon plus 7 for each of the bromines. So it's going to be 4 times 7. And that's going to give us a total of 32 electrons that we're working with. The negative next to the E is just like a symbol for electron. Don't think that that's meaning like a 32 charge or anything. Just 32 electrons. So when we do this to a structure, it's going to look something like this. And we're going to have lone pairs around all of our bromines to give us that total of 32 electrons to make sure that all of them have full valence, all of them have the right number of electrons and have full octets. So on our net dipole moment now, once again, is going to be going towards our more electronegative, which is the bromine. But now this time, we're going to have an arrow for each one, a dipole moment for each of those bonds, which in total is going to cancel out all of them. So we're going to have no net dipole moment, which is going to give us that non-polar molecule. I'll go ahead and do one more of these. I'll do NCO3. So because we already know now that this is automatically our non-polar molecule, but just so you can see one more time with polarity. For this molecule, we know we're going to have 5 electrons here, plus 3 times 7 for chlorine, because chlorine has 7 each, giving us a total of 26. So when we draw this, we'll go ahead and put our chlorines. They're going to have 3 lone pairs each. And now our nitrogen, to make sure it gets to that 5, we're going to put a lone pair here. And because of that lone pair up there, this makes that molecule polar. And everything is not going to cancel out. We are going to have a net dipole moment on here. And actually, the real structure, it even bent looks a little like bent. Okay? So now, number 27. How many grams of water would be produced if 20 liters of oxygen were burned at a temperature of negative 10 degrees Celsius and a pressure of 1.3 atm? So if you had no idea what equation you're supposed to be using for this, we will be using the ideal gas law for this equation. But if you had no idea, you could go ahead and think about what units are you being given. So you know it's asking you for how many grams. So there's going to be maybe moles or mass, something up to that effect being used, because that's what your end thing is. So let's say maybe this is mass or moles, because both of those could be, moles could be converted from grams. Then we have a volume. So we have V equals 20.0 liters. We have a temperature, which is negative 10 degrees Celsius. And when we convert negative 10 degrees Celsius to Kelvin, we get 263 Kelvin. And we have a pressure, which is 1.3 atm. All these units look a lot like me to the ideal gas law. Like that's a big red flag, especially because what we're missing is mass or moles. So that's how you can logic your way through problems. I was just in a final yesterday that the equation literally left my brain. I thought I was never going to find it again. And when I looked at the problem again, I was like, wait, I can figure this out. And I remembered the order of it. So don't let the pressure stop you from doing that. So when we have PV equals N RT, we want to manipulate this problem to change it to solving for the moles of oxygen, this equation. So when you do that, It's going to look something like this. And I'm going to put an O2 subscript next down there so you keep in mind like what you're looking for. It's the oxygen. I mean, you're looking for, you have to find out how many moles of oxygen to figure out the water. So that's why we're looking for the moles of oxygen. Because that's the reactant side here. So this is going to be, once you set it up, 1.3 ATM times 20.0 liters over 0.0821. That's the constant. This is the R constant, and remember that goes back to see how we're using the 0.0821 instead of the 8.314 times 263 Kelvin. It's going to give us about 1.2 moles of diatomic oxygen. Now, it's asking for how many grams of water were produced. So we have to now use the amount of moles that we know we have and this equation to get a ratio. It's going to be 1.2 moles of oxygen times, we have 18 moles of water that are going to be produced. It's going to be 18 moles of H2O per the 25 moles of oxygen. And now we want this in grams, not in moles, so we're going to continue using the molar mass of water to do a molar mass conversion. Which is going to look like this. So in total, we are going to have 16 grams of H2O produced. Any questions? Yeah. Yeah, okay. Well, if someone actually could then check right now, because I was pretty sure that the second time that I actually did save it. Okay, I'm gonna then I'll as soon as we get out of here. We have to finish at 11:50 anyways, because we need time for the other room. So I'll make sure for all of you guys that it is up there. And anyways, I'm gonna post the answers for this, whatever we don't go through. So did that part look good to everyone? It should be on the Study Union WordPress website. Now it's okay. Yeah, did you find the second one too? Yeah? Okay. Yeah, these questions are way more relevant to like so yeah, check again if not. Check with me after, and if not, I'll make sure I could even like send it to you if anything. Okay. So now we're going to use that same chemical equation to figure out if you burned 1 gallon, in here it says 67, but I meant 27. I use a chemical equation from number 27. If you burned 1 gallon of gas and approximately 4,000 grams of that gas, how many liters of carbon dioxide will be produced at a temperature of 21 degrees Celsius and a pressure of 1 atm? So first off, we know we have 4,000 grams of C8H18, which is like from up here. And we're basically going to go through that same process, but we have to think of it for liters. So I'm going to want to go ahead and convert this to moles. Because when we're dealing with gas, we're not thinking about grams or anything. We're thinking about moles, that N factor. So when we convert this to moles, you're going to use the molar mass. 1 mole C8H18 over the molar mass of that is approximately 114.232 grams of C8H18. And you want it to be relevant to the exact amount from this equation. So you're going to continue doing a conversion of this using the amount that is given, because you're looking for carbon dioxide. So you're looking for the moles of carbon dioxide, so you're using the moles the grams that were given to you to find the moles of carbon dioxide with this equation. So you're going to do 16 moles of carbon dioxide over 2 moles C8H18, which, like I said, we got this from this equation. For every 2 moles of C8H18, we get 16 moles of carbon dioxide, which is going to give us 280.13 moles of carbon dioxide. Now, once again, we're using the ideal gas law, and we're going to now, though, because we're looking for volume, we're going to manipulate the equation to solve for volume, which is going to look like V equals nRT over pressure. And once you fill in everything that you have, which here, this is the pressure, 21 degrees Celsius, we're going to change that to Kelvin, so we'll end up with 294 Kelvin, and pressure, and we already have our moles. So you'll go ahead and insert all of that. Get 280.13 moles times our R constant of 0.0821. And if you guys notice, maybe it's because I write quick, but that's one of the biggest mistakes I make, so make sure you don't do that, is trying to put it to 0.821 rather than 0.0821. That throws off your whole calculation, and especially the ACS, they purposely put answers that are based on if you make like a small error in the calculation, something like that. So pay attention to when you're doing that, even in the calculator. Times 294 Kelvin over a pressure of 1 atm, we're going to end up with a volume of approximately 6,764 liters. Okay, moving forward. Any questions on those last 2 questions? Okay. So now it's saying to arrange the following gases at 300 degrees Kelvin in order of decreasing rate of effusion. So if something is lighter, it's going to move faster. And if something's heavier, it's going to move slower in relation to gases. That's like a word of thumb that you could use. So what you would have to do to going through this is get the molar masses for each of these compounds. So we know the diatomic fluorine is going to have 37.900. These are all going to be in AMU. So it's going to be like 37.996. This would be 146.048. CO would be 28.01. And then I'm pretty sure that's krypton, is 83.80. Now, if you want to know in order of decreasing rate of effusion, is the heaviest one going to go last or first? Last. Great. So, which is SF6. So it look like this. Going in order. Now we have krypton, then we have F2, and then CO. Now, here we have Lewis structures. Okay, yeah. Here we have Lewis structures, and determining Mg stands for molecular geometry. She would never put Mg though. She would just put out straight out molecular geometry, and Eg is electron geometry. So for our first compound, we know iodine has 6 times. Actually, we know, I was going to do this in a weird way, but we know both iodine and fluorine have 7 electrons, so you could just multiply them both by 7 times 6, and it's the same thing, but for like clarification purposes, iodine has 7, plus, we know 5 times 7 for fluorine, which is going to give us a total of 42 electrons. So when we're doing this structure, we're going to put the 5 fluorines. These are all going to be filled because we need to get to that 7 and to that full octet. And then when you count what we have so far, you would see that one iodine doesn't have its 7 electrons around it, has 5, and it doesn't have a full octet, and we're missing 2 electrons from our 42. So you could go ahead and add a lone pair there because is iodine after or before the third? Like, where's iodine? What role is iodine placed on the periodic table? Does anyone have their periodic table open? What row? 4? Is that what someone said? 5? Thank you. So because it's 5, it can expand its octet, which is why you could have that lone pair there. And our electron geometry for this is going to, thank you, octahedral. And our molecular geometry is not going to also be octahedral. It's now going to be square pyramidal because of that lone pair. That lone pair now changes our molecular geometry from matching our electron geometry. Great. So now, in our next problem, you're going to do the same thing, except now xenon has 8 plus the 4 for chlorine, 4 times 7 each for chlorine, giving us a total of 36 electrons. When you draw the structure, you'll put the 4 chlorines on, and they're going to have full completely full to get to 7. And now you're missing, xenon needs 8, and right now it only has 4 on it, so you're going to go ahead and add 2 lone pairs. And once again, it could do this because of its placement on the periodic table. It can expand its octet. So once again, you have 1, 2, 3, 4, 5, 6 electron groups. So it's going to have an octahedral and a molecular geometry. Because it has now 2 lone pairs rather than 1, it'll be square planar. Now, this base electron geometry, molecular geometry is just memorizing, how it changes based on lone pairs and knowing how to set up your Lewis structure. Now the next problem is saying which of the following symbols describes an orbital that's incorrect. This just requires knowledge of understanding what L and S equal and how many electrons can be held by each orbital. So we know that automatically, I don't know why this BC. What happens to my A? Okay. Well, can 4, 5 to the 8th, can that exist? Did I hear a yeah or no? Yeah, great. So what about, and I completely skipped over 6S1, but that can exist as well, right? Now, what about 4P8? No, great. And what's making this bad here? Awesome, yeah. So our P can only hold a max of 6. In order for that to be correct, it would have to be like 4F to the 8. Or actually 4D to the 8. Then our next one, this is also going to be wrong. Or, I mean, is this right or wrong? Wrong? Yeah? Okay, well, 2P to the 5th. That can exist, right? Yeah. That's why I asked you guys after I said wrong. And then 2D to the 3rd. Yeah, this one's not wrong because 1, 2 and D will never be together because that's gonna go against the rule of if n equals 2, then what should your L equal? Great. Then your L is going to have to equal n minus 1 or 0, or 2, 0. So that could only exist if it was, if this was 2 to the s, to 2s2 or 2p3. That's how that would work. Now next, this is going through which of the following statements are true and false. As wavelength increases, energy decreases. That sure is true. As frequency increases, energy decreases. That's wrong. Frequency and energy have a direct relationship, so when frequency goes down, energy goes down. So like over here, wavelength, when wavelength increases, energy decreases. So we know frequency and energy are direct, and wavelength and energy are inverse. So this is wrong. The product of wavelength and frequency is a constant. Is that true? Yes, it is true. This is a constant, and that's C equals wavelength times frequency. Then next, as the amplitude of a wave increases, the intensity of light decreases. That's false. We know that amplitude, thank you. Okay. The amplitude, which is the height of a wave, increases as light intensity increases. It's a direct relationship. And then the emission of light results from a transition from lower n to higher n. That's false. Emission is from higher n to lower n, which is the opposite of the problem we did earlier. For absorption, we said that it was from a lower n to a higher n. So absorption and emission are the opposites of each other. Now, this next problem, which probably will be the last, this is dealing with an isoelectronic series, which this is from chapter 8. So here, when we have an isoelectronic series, you cannot just use the trends on the periodic table of radius. You have to think about how they're differing. So we know, well, first thing we're going to do is think about how many protons and electrons each of these have. So bromine's negative is going to have 35 protons with 36 electrons because it gains an electron to get that negative charge. Sodium is going to have 11 protons and now 10 electrons because it lost an electron to get that charge. And Rb is going to have 37 protons with 36 electrons because it had to lose an electron to get that charge. Now, the smaller the number of protons is going to give us a larger radius. And and the same for the other way, larger number of protons is going to give us a smaller radius. So we know out of these, the ones that are the isoelectronic series are the bromine and the Rb, because sodium is completely different. We know automatically sodium is going to be the smallest because it has because it's not part of the isoelectronic series, but we know bromine is going to be greater than Rb positive because bromine has a smaller amount of protons. So when we list this, we use the general trend for sodium. So that gives us bromine is bigger than rhobium, which is bigger than sodium. And now for this last problem, that would just be using what you know from the trends for ionization energy. And ionization energy follows the same trends on the periodic table as electronegativity. So we know that cobalt is going to be the one on the most right, on the most upper right. So this would have the highest first ionization energy. Electronegativity. Great. So that concludes the review. I know there's a few questions from the first one that we are missing, so I'm going to go ahead and put those answer choices up online. These I won't, since we did get to go through all of the second final review. But I'll make sure that